Hello, ladies and gentlemen. This is your force due to gravity notes and inverse square law notes. I have provided capture sheets in class, which I kind of recommend you use because there is a lot of writing on one of the sheets because the inverse square law is not very simple to understand at first, but once you understand it, can help you solve things very quickly with this equation. So this equation, not only do we have force of gravity equals mass times acceleration due to gravity, like I said in class, if you have mass, you have a gravitational pull. So when we have two masses next to each other, we can actually figure out the force of gravity between them, or their force of gravitational attraction. And this is the equation we use. It is in your capture sheet. And so it's F of G equals big G m1 m2 over r squared. So F of G is the force of gravitational attraction. The unit is the Newton. And the big G is the gravitational constant. One moment, forgot to grab a reference table. So the universal gravitational constant is just a value, and it's a constant. It is always that number. Newton calculated it when he did his experiment to determine the force of gravity between two different masses. And so that value is 6.67 times 10 to the negative 11 newtons times meters squared over kilograms squared. Because when we plug all of that into this equation, the kilograms squared and the meters squared cancel out with the rest of the equation. So mass of object 1, which is its units are kg, mass of object 2, which is units of kg, and the distance between the two masses. We use r because it's really kind of a radius, because if you think about planets, they have an orbit around each other, and so the mean distance between the two masses we signify as r, because it is actually kind of like an orbit, because when you have two objects, they really orbit each other when they're allowed to move freely. So gravity is a constant. It's a constant depending on those two masses and the distance between them. Gravity is really small. As you're going to calculate, the force of gravity between two objects is really, really small. Let's see. Gravity is constant. Gravity is small. And I always mess. Oh, gravity is a force that pulls, or an attractive force. So gravity is the force holding orbiting bodies in their orbits. The universal equation reduces to our familiar Fg equals m ag body, ag equation, excuse me, near Earth's surface. And I'm trying to go fast because the next part is going to take a lot more time than this part, because this is just introducing the equation to you. So the equation itself is pretty straightforward. Remember, like I said in physics, if you follow LEPA, everything that we do the entire year follows LEPA. So F of G, the big G is the gravitational constants pulled from the reference table. Then you have the two individual masses and the distance between them squared, which means you can solve for any of these things if you're given all of the other ones. Now, here embedded in this equation is a law. It's called the inverse square law. The force due to gravity has a relationship embedded in it that can help us make calculations easier in some cases. This is called the inverse square law. As the distance between the two masses increase, the force drops by a factor of 1 over r squared. As the distance between the two masses decrease, the force between them increase by a factor of 1 over r squared. So using this equation in math, you can set everything that doesn't change to 1. It's just a mathematical rule. It is the way it is, and it works. Which means that the only thing that we're changing in this equation is the distance between the two objects. We're not changing the gravitational constants, and we're not changing the masses between them. So what we can do is we can set them to 1, because it's just a mathematical rule. I could show you it. It would take me 5 minutes, but I can mathematically show you how if I change the two distances, the other variables don't affect it because they're not changing. They're constant. I believe it's called the law of constants or something of that nature, as a math teacher was telling me what it was called, and I forgot. So what we're going to do here is we're going to fill out this table. And I'm going to say, hey, I know that when the distance between these two masses, once again, we don't care what their values are because they're not changing, we're going to set them at 1 meter apart. And I know the force when they're 1 meter apart is 1 Newton. So I'm going to say, hey, now I'm going to plug in into the equation where f of g equals 1 over r squared. Once again, let me be clear on this. We can do this because big G, M1, and M2 don't change. Since they're not changing, I could say, hey, they're equal to 1. Algebraically, I could set these equations equal to each other. Since those things aren't changing, they will cancel out. So please trust me on this. You don't want the 5 to 8 minute math lesson on this unless you really, really want me to, because you want to be in pain. Anyways, so 1 over r squared. So 1 divided by 1 squared equals 1. So this is the factor that the original force gets multiplied. So the new force is we multiply the original force by this value. So 1 multiplied by 1 Newton equals 1 Newton. That should seem a little obvious. We didn't change distances. That's the force when it is at that distance. Now here comes the fun part. What if I half the distance between the two objects, right? So now I'm just going to plug into this equation. This equals my r now. So 1 over 0.5 squared equals 1 over 0.25. Well, it's really 1 over a quarter or 1 over 0.25. If you plug it into your calculator, gives you a factor of 4. Once again, that new factor, we multiply by our original force, and we see that our new force is now 4 newtons. So if we half the distance, we quadruple our force. And that makes sense, right? If things that are attracted to each other are going to get closer, they're going to pull on each other harder because they're closer, so that gravitational field pulls more. So now let's say, hey, what if we third the distance? So now it's going from 1/2, we went to 1/2 from 1 meter. Now from 1 meter, what if we go down to 1/3? So once again, we just plug into the equation. I get 1 over 0.3 squared, which equals 1 over 0.09, which means when I do the math, I get a factor of 9. When I multiply that by my original force, that means my new force is 9 newtons. So I drop down to 1/3 of my distance from the original 1 meter, and look at that, my force increased by a factor of 9. So now we're going to go the other way. Instead of having my distance, now I'm going to double it. So now instead of being at 1 meter, I'm going to be at 2. So then I'm going to say 1 over 2 squared equals 1/4. So I now take that factor and I multiply it by my original force, and I see here that my force drops by a factor of 4. I doubled the distance, my force drops by a factor of 4 because it's 1 over 2 squared, which gives me 1/4, and that means that my force drops by that factor. And the same thing with tripling the distance, right? 1 over 3 squared equals 1/9, which means that my force drops by a factor of 9. The reason why I'm showing you this law is that in some problems, in some situations, they'll say, hey, the force between two objects is 4 newtons, and the distance between them halves. What's the new force? Well, in this case, if you look at your notes and your charts, I half my distance. My original force was 4. And if my original force was 4 and I half my distance, that means that my force quadruples. So 4 times 4, my new force is 16 newtons. So make an observation about the force as the distance doubles or increases. So if the distance doubles, the force drops by a factor of 4. So let's write that down. The force drops by a factor of 4. And think about that. That makes sense. because if I'm moving further and further and further apart, I feel less and less of the force because I'm further away from it. Make an observation about the force as the distance halves or decreases. And let's just say halves. We don't need to decrease or increase. Let's be just specific. So if I half, it increases by a factor of 4. So the force increases by a factor of 4. So once again, I bring this up because in problems when you're just given the force and you're told how far it's moved, you can use this trick, the inverse square law, to actually quickly get an answer instead of plugging all the points in. Because as you're going to see in class come Monday and Tuesday, that this is a beastly equation, because you have 6.67 times 10 to the negative 11 multiplied by 2.25 times 10 to the 25 multiplied by 2 point something times 10 to the, it's a lot of number crunching or pressing buttons. Now, on the back, I just wanted to rewrite the equation since I don't have this on the sheet. So big G, M1, M2 over R squared. I've already defined these terms, and I want to stop the video because we're at 11 minutes. So I will see you when this is due in class.